Okay. Hello. I want to start by thanking everyone who is, joining us or joining me to watch this talk today. And thanks for all the crew at HolyJS for having me and for organizing the event. I can see how much work there is, or technical work there is, around organizing something like this. But let's talk about my talk. So the title of this talk being Exploring the Hidden Potential of Sound Data, I'd like to start by playing a short audio snippet, and I'm not going to tell you in advance what it is, so you might be a bit surprised because it's very random, but I'd like you to focus on what it makes you think about. All right, so I'm going to play it now. All right, so hopefully you heard this. It was a very short audio snippet. And I think that if it played well, I think that you probably all recognized what this sound clip represents. If you didn't, or if you didn't hear it, it is the sound clip of cutlery, so like knives and forks or spoons. But you might have been a bit surprised because it feels totally out of context. Why am I playing a sound clip of cutlery at a JavaScript conference? Trust me, I wouldn't be here talking to you if it had nothing to do with technology and JavaScript. So please don't leave. I promise that this should be interesting. So as I said, it felt a bit out of context, but actually the notion of context here is very important. Usually in our day-to-day lives, you would expect to hear that type of sound maybe in a restaurant or at home because it is linked to the activity of cooking or eating. So without realizing, you're actually attaching a lot of contextual information to the sound of cutlery. We have the activity of eating or cooking, but that's also, depending on the time of the day, it is linked to three meals, the classic meals of the day. So breakfast, lunch, or dinner. So just with only a short audio snippet that you hear, in your normal life, you attach information, contextual information to that kind of sound. All of a sudden, we know about a location that where we usually hear that sound, an activity, and sometimes even a sub-activity. And this is what I want to talk about today. That's called acoustic activity recognition. So before I dive deeper, I got introduced quickly, but let's just say it again. My name is Gerard. I'm a senior front-end developer at a company called Netlify. And on the side, so outside of my full-time job, I'm also a Google developer expert in web technologies and a Mozilla tech speaker. So if you've never heard of these two community groups, they are tech community groups supported by Google and Mozilla for people who like to contribute to the tech community as a whole. So if you ever have questions about how to get in these groups or what it is, feel free to ask me afterwards, or you can DM me on Twitter at devdevcharlie. So this talk is not related to anything I'm working on at Netlify. At Netlify, I'm actually part of the core front-end team. So I'm helping to build our app that you might be using. But on my own time, I like to experiment a lot with human-computer interaction and researching how we can use technology to find innovative ways to interact with devices and interfaces. We're very used to using our keyboard or our touch screens, but there's many other ways that we could be interacting with devices or interfaces, and I love to research that on my own time. So let's go back to the topic. What is acoustic activity recognition? So it's using the rich properties of sound to gain insights about an activity or an environment. So the same way that your brain was able to classify and recognize the sound of cutlery that I just played and attach some extra information to it, we want to be able to use sounds produced by activities that we do every day around us to classify them using technology. So this type of tech has a huge potential in augmenting smart systems. So this talk is yeah, I had a problem with switching my slides. But so this talk is highly inspired by a research paper that I read on the same topic that was made by the CMU, so this Carnegie Mellon University in the US. If you are interested in the topic, I recommend that you read the paper afterwards. But this talk is about exploring the same space of recognizing activities with sounds, but with web technologies, so in JavaScript. But what this paper tells us is that we could build much more interesting smart systems by taking advantage of sound data. So to gather sound data, we need microphones. And devices with built-in microphones are all around us, from the phone that you probably have with you at all times to your smart home device like Google Home or Alexa. These devices use a microphone, but they don't really leverage the rich properties of sound. Their software recognizes words to trigger commands, but they have no contextual understanding of what is going on around them. Your phone doesn't know that you're in the bathroom, your Alexa doesn't know that you're in the kitchen, etc. However, they could, and this could be used to create more tailored and useful digital experiences. In this talk, we're going to dive into how to build a system to recognize activities. But first, let's take a step back and understand what sound is and how it is transformed into data that we can access with our devices. So sound is the vibration of air molecules. So in the GIF that you can hopefully see in this slide here, the vibration of the speaker disturbs the air molecules around it. That's changing the air pressure that produces sound waves. So for example, if we don't talk about a speaker, but we talk about speech, so when we're speaking, the vibration of our vocal cords produce the same effect. So they vibrate, and it produces the air molecules to move, changing the air pressure, and that creates sound waves. But how can we track that with our devices? So how is it tracked at the moment? So a microphone can detect sound with the help of a thin membrane that moves with the fluctuation of air pressure produced by sound waves. So it transforms the change in air pressure into electrical signals that get amplified and recorded. So there's different types of microphones, but they all have a thin membrane that moves with the air pressure that is produced by activities or objects that produce sound. So usually the thin membrane touches a magnet inside the microphone that transforms the sound waves into electrical signals that we can then use as data. So all of this usually happens too fast for the human eye to see, but the data can be accessed in different ways. And for us, web developers or JavaScript developers, we can get microphone data in the browser using the Web Audio API. So you might have used this API before, but if you haven't, it's okay. The main thing that you need to know is that it can take the microphone as an input and give you audio data as an array of numbers as an output. So in the GIF that you can see on these slides, there's an example of data coming from the Web Audio API that I logged in the console. So what is producing this is a bit of code that gets the microphone as an input, and what you get is an array of numbers. But when you look at it that way, it's difficult to make any sense of it. If you decided to play music or speak or clap your hands, you wouldn't be able to really know the difference based on what you see in the console. Usually, to make it a bit easier for humans to understand this data, we turn it into visualizations. So here, the classic types of visualizations are, you can have a waveform. So that's the white moving line that you see in this animation here that represents the sound waves displacement over time. So sound, as I said, being the vibration of air molecules, this graph shows the oscillation of a sound wave. But again, looking at it, it would be quite difficult to know what's going on or to find patterns in this way of representing data. So another way is called the frequency bar graph, which is the one that's colored on the GIF here. And frequency is a measure of how many times a waveform repeats in a given amount of time. In this way of visualizing, we could maybe start to gain some insight, but it would still be difficult. We might be able to determine how loud a sound is based on the changes in height of the bars, but or maybe we could find some kind of beat or rhythm of like how many times they go up and down, but that's kind of it. A better way to represent this data to find patterns is what is called a spectrogram. And a spectrogram is more of a picture of sound. It shows the frequency that make up a sound from low to high and how they change over time from left to right. So it's a better visual representation of the spectrum of frequencies of a signal. It's a bit like a heat map of sound. So here the x-axis represents changes over time. So the spectrogram moves from right to left and shows new data coming from the microphone as it comes. And then the y-axis represents the frequencies from low to high at the top. And there's a third axis, that's the amplitude. And so the brighter the color, the louder the sound or the frequency. Visualizing sound as a spectrogram like this makes it way easier to extract certain patterns. If we have a look at the one that I prototyped here, as you can see in this graph, there's a difference between the patterns of when I'm speaking and then when I start clapping my hands. You can see that the shape of what you can see on the spectrogram is different. And if you look closely, hopefully you can see on the slides, but just before I start speaking at the very beginning, there's a slight pattern that is repeated. And when I was actually recorded this demo, I had my window open and there was a bird outside and I didn't realize it at first. But then I looked at my spectrogram and I saw this kind of like little like slight pattern. And I then focused, I was like, oh, there's a bird outside. So things that you might not even realize produce sounds because you forget, you can actually also capture them on a spectrogram, which I think is pretty cool. And doing my research for this talk, I actually realized that sound data is used a lot in recognizing and classifying bird calls or certain animals in research. But how do we go from the raw data that we logged in the console using the Web Audio API to a spectrogram? So let's look at a code sample. So we have to start by creating an audio context. And after that, we call the get user media, that's the native browser API, that gives us access to some of the computer's hardware. Then we indicate that we want to have access to audio data by passing the parameters audio true. If you ever want to also use the webcam for one of your projects, you can also pass the parameters video true, but in our case here, we don't need it. So we can just, just pass audio true. And then we have access to a callback that gets access to the stream object that contains our audio data coming from the microphone. Then we use some of the Web Audio API methods to create an audio source to which we pass our stream of raw data. Then we create an analyzer node and we connect our analyzer to our source. If this sounds a bit complex, don't worry. I find the Web Audio API a bit complex myself if you don't know much about audio analysis, etc. But the main things that you need to know if you want to build something like this is that the steps of setting an audio source, an analyzer, and connecting the two together. If you want to do something with the Web Audio API, you will need at least these steps. And then I have created a function that I just called get audio data, but you can call it what you want to do something with the data that we get. So in my get audio data function, what I do is that I use the frequency bin count method on the analyzer object, and I call the get byte frequency data method to extract the frequency data. So these are also Web Audio API methods, but that allow us to extract the frequency data from all the raw data that we get from the microphone. Then when we actually have access to the frequency data, the way we're going to draw it is with some canvas methods. So we use the canvas methods to fill our canvas with our visualization. So I get image data to get what is already on the screen, and then I put a new image data to kind of like show it as it moves. And I loop through my frequency data. And I determine the color of each stroke by using the stroke style, using the values coming from the frequency. And then I use the move to method to move each stroke by 1 pixel to have the feeling of visualization that moves over time and that can draw new data coming. And then the line to just like, and stroke draws the actual line on the canvas. And then you have to remember to use the request animation frame function with the name of the function that you want to call repetitively to draw the latest frequency data coming from the microphone. All right, so the result, as I showed earlier, is this spectrogram. So we can pretty visibly see the signature of different activities. But for now, this spectrogram only visualizes sound in real time, but it's not doing anything else. It's a very helpful tool to see that if it's even worth going further, because if all the signature of sounds looked the same, even to the human eye, it would be hard for a machine learning model to be able to extract patterns. But if we can even see it on the spectrogram that they look different, we can hope that a machine learning model would also be able to recognize that. So our goal is to be able to classify these sounds to automatically recognize activities done by a person. So this is where we can use machine learning to train a model to find these patterns for us and build an activity classifier. So in the research paper that I mentioned at the beginning of the talk, done by the university in the United States, they showed how different activities have a pretty distinct signature. That means that hopefully after some training, a machine learning model would have no difficulty classifying activities. So for example, here I highlighted one on the left that's water running. So if you just kind of have your tap on, and the spectrogram of it or the signature of that sound is quite different from, for example, what a microwave sounds like when you're open or close the door, when it's actually heating up some food. So you can have a look later if you want at the different other activities, but we can see here that some of them are quite different and would hopefully be quite easily to distinct with a machine learning model. So we could be using this information to augment our IoT home automation systems to know if we're currently cooking or doing the dishes, or if somebody's knocking on our door, or if our doorbell rings and things like that. But how would we go about building the recognition system? So to do this with web technologies, we're going to use TensorFlow.js. So if you've never heard of it before, it's a JavaScript framework based off of TensorFlow, developed by Google, that is originally in Python, but now can also be used in JavaScript. So to build experiences using machine learning in the browser. So what we're going to use as well to make it simpler is an experiment built by one of the parts of Google, one of the teams there, that's called Teachable Machine. So this interface allows you to record sound samples, train and export a model super easily through the interface. So what usually happens is that you have to start by recording some background noise that is going to be the reference of, when there is no particular activity, this is what my kind of like soundscape around me sounds like. And then you can record different samples that you label. In the animation here, I was snapping my finger. I'm going to try to do a live demo of this just after. But then, yes, so you can record a few samples and you can train and you can preview. So I recorded a GIF, and yes, it's not working live, but I'm just going to switch tab and hopefully it will be working as well. So just before this talk, I recorded the background noise for 20 seconds. I did it in advance because having a 20 seconds pause during a talk would feel like forever. And it would be a bit boring for you as well to just sit there and do nothing for 20 seconds. But so here we have the spectrograms of what 20 seconds of just background noise with nothing happening around me would sound like. And then here what you can do is I can edit the label, and I'm going to call it snap because I'm going to try to record while I'm snapping my finger. And if it works, my browser has been open for a while, so hopefully it's going to work. But if I stop talking and record snap, so So here you can see a sample where hopefully you can see, or I will show you I will share the slides later with the link if you want to try it yourself. But you can see the signature of snapping my finger, so I can extract that. I'll do it again. I have to do it 8 times minimum. Almost there. All right, so I have my 8 samples minimum here. You can train a lot more if you want, but if you just want to test it out, it's 8. And then I could also add another class if I wanted to, so you can train whatever produces sound. But then you can train it live in the browser. So, and it actually doesn't take that long. This is what I really like about this experiment. It trains the whole model with all the samples in the browser live. It just takes a few seconds. And then what happens is that it tries to detect live in the browser the sound. So at the moment, as I only trained background noise and snap, when I'm speaking, it's a little bit confused. It doesn't really know what's going on. But if I stop, it should put background noise to 100%. So I'm going to try that. So as you can see, if I stop talking, it knows that it's background noise. And if I stop and I snap my fingers, every time I snap, it actually puts snap to 100%. If I was training the model to recognize speaking as well, then there would be another label and it would be able to recognize that. So, and I'll show you that later with another demo. But basically what happens then is that you can export your model with your 2 classes of background noise and snapping, and you can use that in your app, but I'll talk about it just after. So let me go back here. I'm going to close that. Oops. Yes. Okay. Okay, but so how does it actually, you might be wondering, how does it actually do this recognition? How does it work in the background? So in the background, it uses a convolutional neural network algorithm that is used to classify images. So why images? Because we're not feeding raw data directly to TensorFlow.js, but instead we're using snapshots of the spectrogram to run our training and recognition. Spectrograms represent way less data to feed to an algorithm than sound data raw from the microphone. So the default sample rate of the Web Audio API is 44 kilohertz, which means that it collects 44,000 samples of data per second. If we record 2 seconds of audio data coming from the microphone, it's about 88,000 points of data for a single sample. So if I was just recording snapping my finger once, it would be already 88,000 points of data. So you can imagine that as we need to record more than only one sample, it would end up being a very large amount of data being fed to a machine learning algorithm, which would take a long time to train. So on the other hand, a spectrogram being extracted as a picture can be easily resized to a smaller size. So you can see that in Teachable Machine, the spectrograms were very small. They didn't take the full screen as the one that I built. So a spectrogram can be easily resized and you could still see a pattern. So it means that in the end, we could end up having a spectrogram that's only, for example, 28 by 28 pixel as an image, that would only be 784 data points. So this is why I put this example here on the slide, this animation, where if we had a spectrogram that was a small image of 28 by 28 pixels, it would be 784 pixels in total that you could feed into different layers of convolutional neural network, and that would be much faster than training a model with audio data. So at first I thought that they were using raw frequency data from the microphone, but then I realized that I was wrong when I went into the source code of TensorFlow.js and of this particular model. And you could see that they actually write in the comment that they use a spectrogram. And if you look at how they created their model, they use the conv2D method, or to create the like all layers in the machine learning model, which is convolutional neural network for images. But another important thing as well is that the Teachable Machine experiment uses what is called transfer learning. And I could see that because in the code, they use the method add example on the dataset. So let's talk quickly about what transfer learning is, because it's a type of machine learning or a type of learning. So transfer learning is a technique where a model trained on one task is repurposed on a second related task. So in our case of sound recognition, the machine learning model used in TensorFlow has already been trained with many samples of audio data. And the experiment of teachable machine takes a new sample that we record ourselves, and it repurposes the original model to be trained with new sample data. So we are not, so that's probably, I mean, that's why we have to only record a minimum of 8 samples, because usually in machine learning, if you want to do everything from scratch, you have to record a lot more than 8 samples. So here they already trained it with many samples of audio data, and we're using transfer learning to only add our own on top of that and retrain the model with this. So now let's look at how we would use the model generated, so the one that we can download after a teachable machine in our code. So what we need to start, we need to import TensorFlow.js and the speech commands model or library. So that's the one that is used in the experiment. So then once we actually required what we need to work with, we have to declare the path to the model JSON and metadata.json file that we downloaded from the experiment. So the model is the model itself, and the metadata includes quite a lot of things, but I know that at least it includes the labels of the things that we trained. So we have the path to the files that we need, and then we can use speechcommons.create, and we pass it a few different kind of like signal processing algorithms. So this one is the browser FFT. There is another one, but last time that I tried, it didn't work. So browser FFT works fine. And then we can pass our model and our metadata URL. And what is important to remember is that it's good to call model.ensure model loaded before we keep going with our experiment, to make sure that the model is loaded before we go further. We can also pass a few different parameters if we want to include the spectrogram data to visualize it. Otherwise, you don't have to, and a few different ones. But you can have a look at that later if you want. And then finally, we call the method to listen to live data from the microphone. And every time it detects a certain sound that it can classify, it calls the callback with the scores that it gets from the prediction. And then when we actually call this data, we can declare our labels in our file. So it could be anything, but it has to have at least the background noise. And when we call this method, we pass the URL and the data, and we can have our, so the way we get the prediction at the end is an array of floats that are from 0 to 1. And the closer the prediction to 1, like the highest. So if I have the labels here of clapping, speaking, and background noise, and we get an array of 3 floats, and one of them is 0.8, then 0.8 is what has predicted my activity to be. So this is how you would train some audio samples and a model with teachable machine and export it and use it in the app. But now let's cover another way that you can get new sample data with the transfer learning API. So I think this is quite new, and it allows you to kind of do the same process, but without having to go to teachable machine to do it. You can actually do that in your app. So they're providing now an API that allows you to embed the training process in your potential application. So if we looked at a very, very basic example, here is just a screen with 6 buttons. 3 of the buttons would recognize the words red, blue, or green. Then the background button would just record the background noise. Then we have a button to train, and finally a button to predict. So very, very simple interface. I'm sure that if you wanted to build that, you would build something much better. But in terms of code, what we would need to do to be able to do the training ourselves in our application, we would, again, call speech commands, create browser FFT. We, again, ensure that the model is loaded. But then we have to create a kind of collection of samples that we decide to train. So here we can call, on the recognizer, we can create a transfer that I called colors, because what I'm training is colors, so red, green, blue, but you pass whatever string that you want. If you wanted to detect activities, you could just label the activities. So you have to start with that. And then when you're sure that the model is loaded, you have just some normal, I don't think I really need to go over this, but just some normal DOM APIs to get your buttons element. But the important thing here is that when you click on the button, you can call transfer recognizer.collect example, and you pass it the label of the example that you're currently recording. So that then when you click, it knows what label and it can attach it to the live audio that it gets from the microphone. So here I have red, green, and blue, and I have one for the background noise as well. But here, once we're done recording, so you can click these buttons many times and it will record live and attach the right label. But when you run the train button, you can just console log the amount of examples that you trained, just in case, if you want to make sure that you have the right numbers or anything. But the important part here is then the train method, where the epochs is the number of steps in the training. Here it is 25. That was the base number that was in the README of their repo. I didn't change it. But if you feel like your accuracy is not good enough, you might want to change that number to have more or less steps. And then every time that one epoch ends, so every time that one step ends, you can console log the accuracy to see if it is the closer to 1, the better it is. And then when you actually did the training, you can click on the predict button. That will again listen to live input from the microphone. You can get the word labels, which are the labels of the samples that you just trained. So here my words would be red, green, and blue. And you look through these words and you look at the score, and the closest to 1 is the label that I actually just said. So if I was in the browser and I just clicked on predict and I said red, then the label, the probability for the word red should be the highest, and it should be logged in your application. You can pass it a certain probability threshold. So if it's here, it would actually give me the scores only if it's over 75% confident that I said one of the words in my labels. If you want it to be super accurate, if you don't want to have any false positives, then you could change it to 0.9 if you wanted. And then finally, you can have a set timeout when you don't want to listen to the microphone anymore, when you pass it a certain amount of seconds. There's a few other methods as well that you can call if you want. You can export the examples that you trained in your application as well. That contains the spectrogram data that you can then use with other code if you want as well. And then if you want to export them and use them in another application, you can use the load examples method. Okay. And now there's even another way that you could do this quickly, is if you want to do it offline. Because at the moment, when you're listening to new samples from the microphone, if you don't want to actually stream that and you want to only do it offline, there is a way that you could do this, and it's a pretty short code sample. So you also have to require TensorFlow.js and the speech comments model. You still have to call speechcomments.create browser FFT to initiate the recognizer. But then instead of calling the listen methods that's going to be streaming and listening all the time, you can create a tensor that's like a data type in TensorFlow.js, but you have to pass it your own spectrogram data. So this is where you could actually export it from the transfer learning API and actually feed it to a tensor and do everything offline. So that would be like the training, and then you would recognize based on the spectrogram data that you fed it here. Okay. So now that I talked about a few different ways to do this, I thought that I would show you a quick demo of where I ended up with my with this project, with a few activities that I trained. So hopefully it should work. Okay, so here is my demo where I'm going to start, and I have a few labels that I trained here on the left. Hopefully I might have to refresh my browser. Yes, I think I do, because, okay, I might have, oh, wait. Is it work? Yeah, okay, sorry. Okay, so I think the model just took a little bit of time to load, but as I'm speaking, it's recognizing the activity of speaking. And if all of a sudden I stop and I cough, So it recognized the pattern of coughing, and I also trained the phone ringing, but I'm not going to do it here. But if I it also recorded the sound of typing on my laptop, but just because I don't want to have any mistake with my slides, I'm just not going to do it now. I don't want to press any wrong key. But one activity that I did was brushing my teeth as well. So I'm going to try to do it now with a clean toothbrush, but let's see if it recognizes. Yay! Okay, I'm gonna have a bit of water now because it was gross. But you could see that the pattern of the sound of me brushing my teeth is quite distinctive from the rest of my activities that I trained. So you could see that I have some false positives in some activities that it recognized. That is mainly due, so you know how sometimes it recognizes that I'm speaking, but sometimes it will say brushing teeth for a second or phone ringing like now. I'm going to stop it here. I'm going to go back to my slides. Okay. Okay, cool. So yes, so what happened here is that I used the Teachable Machine platform, and I trained a small number of samples of different activities. So if you want it to be more accurate, you will need to create more samples, but it was just a prototype. So it's normal to have some false positives if I only trained like maybe 10 samples per activity. If I wanted it to be 99% accurate or accurate 99% of the time, I will need to train it more. But what is important here is that I didn't record the samples in this particular apartment. That demo, I built it when I lived somewhere else, and there was another kind of background noise. And this is where the power of this technology is quite interesting, because I recorded samples in a different environment, and I gave this talk once before in another environment, and now I'm doing it here, and it was still able to recognize kind of accurately my activities, even if I'm in different environments as well. And what is interesting is that I didn't brush my teeth the same way as I did when I recorded, or the words that I'm saying are not the same. And this is where it's not recognizing the words, it's recognizing the pattern of speech, which I think is like super cool. And for the purpose of this talk, I built a demo with only these activities, but in the research that they did, you can see that you can train and recognize a lot of different activities. You can have different appliances. Yes, as humans, we know the sound of the toilet flushing, or you know the sound that your microwave does when it finished, heating stuff. So if we can recognize it, we can also feed that to an algorithm. But also what I like as a front-end developer and doing that in JavaScript is that it can run on multiple platforms. I'm showing it here on my desktop or on my laptop, but as it's in JavaScript, it also works on your phone. I've had some issues with cross-browser compatibility. So depending on the browser, there's going to have some weird stuff, but that can be fixed. This is just because I didn't spend the time on fixing it. But so you can run it on your laptop, on your phone, but also on IoT devices, because now in Node.js, you can do like JavaScript everywhere, basically. And one example of that is that if you'd like to tinker with it using Raspberry Pi, there is a voice kit by Google that you can make, kind of like make your own thing. And I put here the link to the repo. So Ubiacoustics is the name of the project from the research center. So they did open source what they were doing to be able to run on the Raspberry Pi, but it's in Python. So if you're interested in learning Python or trying it out, you can. Actually, I think I even tried it on my laptop. You can run the Python example on your laptop as well if you want. But you could recreate the exact same thing in Node.js. That's the point of this talk, to show that even if it's done in Python in the research center, you could use the same concept and do it in JavaScript. Another really cool example is that now the TensorFlow.js team is actually working on different models that you can run on an Arduino. And if you've never played with an Arduino before, the amount of memory that an Arduino has is usually quite small. And the fact that you can now run a machine learning model on an Arduino is really cool. So the only kind of like downfall is that the micro speech example, which is an example that does the same thing as I'm talking about here, but on an Arduino, can only recognize the words yes or no. So it is pretty small, but it's still really impressive that so like a lot of people are working on making that happen for IoT devices. So this board, that's a Nano 33BLE Sense, one of the newest Arduino boards. It has a lot of sensors in it already, and it has a microphone. So you can run this machine learning model on the Arduino to record directly. So you can use the microphone on the Arduino, record samples of saying like yes or no, and have and do anything you want with that, knowing that with Arduino, you can use Node.js to turn some lights on or do whatever you want, really. It's really cool that you can now not only do it on a web page, but also on devices. Okay, so let's talk a little bit about the benefits, because I talked a lot about the tech and how to build it. But one of the main benefits that I see for that kind of project is, as I said at the beginning, is to augment smart systems. And what I mean by that is that with only one device, is that you don't have to buy a smart fridge anymore, or a smart microwave and a smart coffee machine and all of the smart things that that cost a lot of money and that only know about themselves. If you buy a smart coffee machine, it doesn't know if your fridge is open, or it just knows if the coffee machine is on, or it might know what time it is and it sends you a notification, but it doesn't know anything else about your environment. Whereas with this kind of technology, with only one sensor, you could recognize a lot more activities, and it doesn't cost that much money, and you can train it yourself. And I think that it's a lot more interesting. Also in this talk, yes, I showed a few basic activities, but because I can't really bring you to my kitchen and try that with the fridge or something, but you could really train the algorithm to recognize any kind of pattern around your house. So let's talk about a few applications for that kind of technologies, because I think it's pretty exciting, and there's some applications that you might not realize are actually already out there. So I talked a lot about augmenting smart systems at home, but some examples that you could do with that is you could recognize if people are in a room in an office by listening to certain sounds of activities like typing or talking or opening the door of a meeting room, instead of, because I know that sometimes in systems like Google Home or Alexa, a lot of offices don't want to use these devices for privacy reasons. You don't want Google to have access to whatever you're saying in meetings and things like that. But if you build your own, or if you switch it to recognizing activities instead and not words, and you can build this this system yourself in JavaScript, it means that you can still build a smart home or a smart office without the concern of privacy of knowing exactly what you're talking about. All you might know is that there's a person typing in a room. That's a lot less invasive, I feel. But there's also applications around if you're cooking while watching a video on an iPad, for example, you could play, well, you could pause the video as you're cooking without having to touch anything. So if a recipe was like, oh, now chop some potatoes, it could listen to the sound of chopping, pause the video automatically, and then keep moving, and you wouldn't be able, it would kind of like it would be a smarter way to cook, for example. But then another application is around interactive storytelling, and that is more how you could implement that is in some of your work. If you're working more towards, if you're in a creative agency, for example, if you're working around making interactive websites for advertising campaigns or something like that. You could have that kind of technology. I used to work briefly at the New York Times, where my role was to make some pieces of content more interactive for people to read, to kind of like make people more interested in reading content. And I see that kind of technology would be really interesting. You could have that kind of exchange between a piece of content that a user reads, and it will be waiting for the user to actually engage with some sounds, like the sound of like knocking or like anything really, or clapping your hands or something to trigger activities whatever. And then finally, in terms of health tracking, I trained my demo in recognizing coughing, but you could also do like sneezing or snoring or whatever. I think that in the recent COVID-19 pandemic, some people have been actually looking at this activity to recognize the sound of coughing and, tell you to be careful about your health. So these are just activities or applications that I could think about when I was thinking about my environment or how I would use this. But there's actually applications where it's already used. So an example of this is for an organization called Rainforest Connection that partnered with Google to create a project that prevents illegal deforestation. So they actually used old Android phones that people were not using anymore. These phones have microphones, and they recorded the sound of a chainsaw. So when people are about to cut some trees, and they attached these phones in multiple places in the rainforest. And as soon as it detects the sound of chainsaw, it alerts rangers so that they can go and stop illegal deforestation. So I thought that was a really cool application of such a technology, and that's why feeling like I can explore the same space in JavaScript is super interesting to me. Another example is in acoustic monitoring of different kind of animals. So you have a lot of biodiversity researchers that are looking at identifying certain animals in the ocean, especially because you can recognize how the songs of different kind of whales, to know how, I think in New Zealand it's used a lot to know how many different species of animals are in the ocean at a certain time in the year. And what you could do as well is you could detect certain ships that go in the water, so you could stop illegal killing of certain whales as well. So you could really use that kind of technology in research. But another example that you might not be aware of, that you might have actually come across, is in YouTube. So it's live captions, but not live captions of words, live captions of ambient sounds. So sometimes, I don't know if you trigger the captions in the YouTube videos, but when you have the transcript of somebody speaking, sometimes you also have in square brackets the transcripts of the sounds. So I think at the moment they have that when an algorithm detects that music is playing, you will have music in square brackets. If in the video there's somebody applauding, then you will see that in square brackets as well. So they've used a lot of videos that people have uploaded on YouTube, and they've extracted certain sounds that activities make to be able to give kind of like more interesting captions to people who use captions all the time. Because if you're in a space where you can't hear, or if you're hard of hearing, if you can't hear very well, you usually use the captions in a video. And by adding that contextual piece of information, like people are applauding or something, you kind of enhance the experience of people who use captions a lot. So that is currently used in YouTube, and it actually was implemented in 2017. So that they've been looking into that kind of technology for a while. And more recently, actually this week, Apple in their conference that is going on this week released an update in their Watch OS. So if you have an Apple Watch, now it has water detection when you wash your hands for COVID-19, where it will trigger a counter for 20 seconds when it detects that you're washing your hands to kind of tell you when you're done washing your hands. So there's a counter of 20 seconds. So it sounds like something small, but I was quite excited to see that people are really trying to bring that idea to production into devices or interfaces that people actually use. And when I saw that it started being shared on Twitter, I liked that I understood straight away the technology that they were using, because I've been researching that. So it might be using as well some sensor data for the movement of the hands, but it starts when it recognizes water. And what was fun is that as I knew how they were building it, I kind of built a small prototype of it in just a couple of hours, as I had played with that before, and I understood and I knew that teachable machine, and in a few lines of code I could build the same thing. Obviously, I don't have an Apple Watch, so I used my laptop instead. But it means that I released that. There's the link if you want, or I'll share the slides later. But that works on the phone, and that works on your laptop, on your iPad as well, if you want to use it. But it means that in a few lines of JavaScript, I was able to prototype something that Apple pushed to production. Of course, mine probably has some false positives a bit more. Theirs is probably more accurate because they released it. But I thought that it was interesting to be able to reproduce the same thing, but in JavaScript at home in a couple of hours. So, everything is cool, but there's some limitations. So if you get into that space, I want to talk about some of the limitations for this. So you need lots of sample if you want to do everything yourself. So if you don't use transfer learning, and you don't want to use teachable machine or anything, if you want to do everything yourself, you will need lots of samples of sound. 8 samples, if you do everything from scratch, are not going to be enough. Then the quality of the samples is important. You have to be in an environment where you can record that particular sound that you're looking for. If you're recording a sound and there's a lot of background noise, it's not going to be a very good quality of data. Then the model file size can be very large, depending on how much data that you train your algorithm with. The model can be quite large, and it will impact the experience that you build. So if you download a model that's, for example, 15 megabytes, that happened to me before, of course, you will have to rethink the way that you build your website, because loading 15 megabytes is huge. You might have to rethink how you do this. Another one is that it's not always able to understand multiple activities at once. As you could see in my demo, sometimes it was a bit confused if I'm speaking or coughing, or if I was speaking and in the background there was the TV playing or something. It's not always able to recognize or to extract only one activity. So it probably will get better over time, but at the moment it will recognize the activity which probability is the highest. And then finally, privacy. I know that people feel weird about having Google or Apple know about their activity all the time, but also, if you have a Google Home, or even if you have an iPhone or a Google phone, they are already listening to your activities, or to your words, and I would rather them listen to me washing my hands rather than everything that I say. But even if there are limitations here, I want to talk about a few ways to go around them. So in terms of privacy, there's a project called Project Alias that is a kind of do-it-yourself project. So there's a web page. I have the link on the next slide, but it's a project made by someone that is a dev. And you can 3D print the case at home, but it uses a Raspberry Pi underneath. And what it does is that you could put this device on top of a Google Home or an Alexa, and it will block signals, or it will block the Google Home from listening. And all it will do is that you have an app on your phone as well, and you can record your own trigger that you want to use to turn on your Google Home. So what it does is that it sends white noise to the Google Home, so the Google Home is not able to listen all the time anymore. And you can write your own program to trigger that little device only with a certain sound, and that will then trigger the Google Home. So you're kind of blocking signals from the Google Home, and only really when you want to trigger it. So if you wanted to use that for activity recognition, I could train that little module to only recognize the sound of me brushing my teeth, and then it would trigger the Google Home. So if you're interested in protecting your privacy, that project is pretty interesting. And here's just the diagram if you want to put it together, where you have a 3D printed shell, a microphone, a Raspberry Pi, a speaker that sends white noise to the Google Home, and then there's details about the app and how to train your own samples as well on the site. For being able to detect multiple activities, there's another project I'm super excited to try. I haven't tried it yet, but it's called General Purpose Synthetic Sensors. So it's instead of using only the microphone to build spectrograms and recognize activities, they've actually built the little module that's on the right here that has multiple sensors. And for example, you have a color sensor, an accelerometer, also a microphone, and a motion sensor. And you can use data from all of these sensors to build multiple spectrograms and use that to make your activity recognition more accurate. So you might be able to detect multiple things at once instead of only using the data coming from the microphone. So I think that this is really cool, and I know that they probably haven't built that with JavaScript to start with, but I think that it's possible to probably build the same thing with an Arduino and use Node.js to actually get the data and build spectrograms and being able to do a multiple activity recognition at once. If you don't want to build your own device, you might be able to actually play with an Apple Watch or an Android Watch if you have one, because these devices have multiple sensors as well. They have a microphone, but they also have, I think, so they have accelerometer and gyroscope for, to be able to detect movement. They also have a magnetometer, if I'm correct. And you probably would be able to get this data as well from different sensors of your watch to recreate or to play around with the same kind of experiments. And then finally, for to go kind of against the limitation of having to record a lot of samples yourself, there's another exciting project that is like, I saw it when I was researching for this talk and I got super excited. It's called Listen Learner. And it's automatic labeling of and classification of sounds. So it's a collaboration between the CMU University and Apple to basically have a device. So I find that even more creepy though. But so the device listens all the time, and it listens to the sounds around your house. And then when it detects something different from the background noise, it will start to put it into clusters, like the visualization on the bottom right here. So you go about your life, you do your thing, and it automatically kind of record different samples of noise. It clusters them as similar noises. And then when it has recorded and clustered enough samples, it will start asking you. So if you repeat, if you open your microwave door again, it will be like, what was that? And then you say, oh, it was the microwave. And it will attach that label to the cluster of sounds that are similar to the microwave. And it does automatic labeling so that then when you open the microwave door again, it will know that it was the microwave, and you wouldn't have felt like you had to record everything yourself. It was just listening. So that's more creepy because it's really listening. But I think that the research around it is really interesting. So I would love to try to do that at home, and having to have my machine learning model cluster things automatically and being able to create interactions like that. Okay, that was a lot of info. So just before I finish, I just want to recap a little bit the different steps. So first of all, you have to collect audio data somehow. Either you can use the Web Audio API if you want to do it in the browser. Otherwise, I know that in Node.js, I think there's some modules that allow you to have access to audio data as well. So you just have to collect audio data somehow. Even if you want to download there's probably open source collections of sounds as well. I didn't really research any of that, but you probably could find something. Then you have to build spectrograms from this data. Then you have to use machine learning and train a convolutional neural network with TensorFlow.js to kind of find patterns in these spectrograms. And then you can use the model generated either in web or either with JavaScript on the web or in Node.js. I didn't really talk about TensorFlow.js in Node, but you can do the same in Node.js. So I'm just before I finish. I hope that you're as excited as I am about the potential of this type of research. But if you're a bit skeptical, I understand, because I know that sometimes people don't like that companies might be listening to what you're doing, or you might not see how this technology is interesting. But what you should still be looking at, in my opinion, is that the main researcher that worked on the paper that I mentioned at the beginning is actually now working at Apple. And I'm pretty sure that he probably contributed to the update to the Watch OS that detects the sound of water. So I really think that in the not so far future, this type of tech might actually be used in your laptop or in your phone, or more applications on your smartwatch, because our devices already have microphones. We're not waiting for any hardware update or upgrades. We're probably only waiting for the right application. And that's why I was excited about the washing hands. It's a small thing, and you could think, well, I can count 20 seconds by myself. But I think that what Apple is doing is they probably know that it's not the best idea ever, but they're probably testing that type of technology to see how are people comfortable using it. Is it accurate enough for us to keep doing that kind of research? So I don't want to speak for Apple, but I like to see that Google has been doing a few experiments with sound as well. Apple is doing it, and I'm sure that other companies that I might have not seen are doing that as well. And my excitement about it is that we can explore that space with JavaScript. So even if we don't have access to a research center, or we don't get to work with Google or Apple, if we understand how this technology is built and we can do it with JavaScript as well, we might be able to contribute to the same kind of research and understand and maybe think about different applications for the future. But anyway, that was it. Thank you so much for having me. And if you have any questions, I'm still going to be here, and I will share links on Twitter at DevDevCharlie a bit later if you want some resources and some more info, or if you want to look back at some of this information. But thank you very much for your time and attention.
Thank you very much, Charlie. Since my master degree is exactly in artificial intelligence, it was a big pleasure to listen to your talk. First of all, as far as I understand, we are not working with sound as a sound. We are working like with a three-dimensional data, so or whatever, n-dimensional data. So as soon as we adding more and more sensors, our, let's call this image, it becomes bigger, and you can't even put it in your mind because, well, I'm bad in imagining 4D cube or 5 dimensions cube. But my question is how adding additional dimensions to our model, how quickly it becomes a computational hell? How complexity of the model raises when we're adding additional dimensions?
I wouldn't be sure about that, because at the moment my experiments were just with like the audio data. So I think I might have an answer for this once I search more with like more sensors or things like that. I haven't read, because they also wrote a paper about their general purpose sensing technology, so that uses all the different senses. So they might have the answer in the research paper, but I haven't read it yet. If I get to work with that in JavaScript, I'll share info about it. But I think it might be a problem, but I haven't encountered it yet. Or maybe I will just give up and not do it at all. But but yeah, it can easily become just something too complicated. But I wouldn't know like the exact answer to that question right now. But I think it would be an interesting thing to research.
Yeah. Another question is, you've demonstrated recognizing like a short series of sounds or a specific patterns. Like you are really awesome at clicking with your fingers. I'm a bit jealous. I can do that that great. But what if we have like how long this could be the sequence or the pattern to be recognized? For example, what if we try to recognize maybe some songs of specific group, or music band, or whatever with such approach? Will it work?
I think that because I was researching, I think I was because I think I don't know if you remember the app Shazam that recognizes songs automatically, and they kind of use the same technology. The issue with having really long like songs is that it's a lot more data, and I don't think that it might be too much data to feed to an algorithm to recognize an entire song. I think that in songs there might be some features that you want to extract, like maybe a rhythm or a type of instrument, or I'm not an expert in like audio analysis, so I wouldn't know entirely for sure, but I don't think that you would want to feed the entire song. I think you would want to do probably some kind of signal or audio processing to extract certain features that are quite different from one song to another, and then use that to differentiate different songs. But I don't think that feeding the whole song would be useful. I think, for example, I would maybe assume that the voice of the singer would be in different frequencies depending on the band. So maybe you could use that, or maybe one band has more hi-hats in like their drum sets than others, or some bands are more metal or pop, or I think you could be able to easily recognize the type of music just by having little snapshots of a spectrogram. I don't think that the amount of data that you would have to gather to, sorry, my neighbors are making a lot of noise. I hope you don't hear that because it's annoying. But yeah, I think that an entire song would not be worth it. I think it's the same thing as when you play with other type of data, because what I didn't actually mention is that this type of technology to use spectrograms can be used with a lot of different data. So you could, here I used audio data, but you could use data from Arduino, like the example that I showed at the end, but you could also use a brain sensor data that I'm also doing on the side, where all the data might not actually matter. It's about extracting the things that are different from your other samples. So I don't know if I'm explaining that super well, because I've only worked with small samples, but I don't, I think you would have to do some audio processing to extract certain features of the song and train that instead of feeding the whole thing. I think the sample would be too big, and I don't think it would be worth it. But then how to analyze which segments to feed to the algorithm, I think that would be more of a play and see what happens. But that would be worth doing more research about that as well.
Thank you for such a detailed answer. We have a question from from our colleagues. Dimitri is asking, do you know any application for recognizing birds by their song?
Yeah, so actually, so I know that they do that in research. There was a book I wanted to read, but I forgot the name. But there's actually an app that's called BirdNet that I have on my phone, and it has that actually. So you can record I don't know if it's on iPhone, but I know it's on Android. So it's called BirdNet, and you can record live when you're outside sounds of birds, and you have the spectrogram on your phone, and I think that it can tell you the type of bird based on the spectrogram, which is pretty cool. Like, there's not that many birds in Amsterdam, so I couldn't really try it, but I used to live in Sydney in Australia, and you have some birds that are like, you can really hear them a lot, and I wanted to try that when I go back, when we're able to travel again. But yeah, I know that it's used in research, and the only application I know at the moment is called BirdNet. But otherwise, there might be there might be others that I don't know about, but I thought that it was a pretty cool thing.
Yeah. Another question is how hard is for you've talked about running some analysis from Raspberry Pi or running from some low power device. How hot my laptop will be if I will be running your demo for a few minutes?
Well, I think my laptop is quite hot right now, but there's a lot of things going on. So it depends, because when the demos that I built, I have run them on my phone, for example, and so it drains the battery a little bit. But yeah, that's why you wouldn't want to run that kind of things like all the time. But I haven't tried yet on hardware like the Raspberry Pi or the Arduino. I really want to look into that. But I know that for the phone and the laptop, of course, at the moment it still drains your battery, because it depends on how long your training runs for, but it's still quite expensive in terms of like computer, I don't know how to say that, not energy, but you know what I mean. It needs quite a lot of computer power to run a model. I remember that sometimes in some experiments that I did a while ago, my training process was taking 8 hours because of the data that I was using, and that obviously you need to have your laptop plugged in to be able to run that, and that was quite annoying. I haven't done that in a while. I think at the moment my training process for the experiments that I've been doing were quite short, so it was all right. And if I run them in the browser, at the moment my experiments are pretty short term, so I don't have to run it like the whole time. But my phone sometimes gets a little bit hot, but then you just close the browser, it's fine. But yeah, I think as the tech gets better, things are going to be faster, and they're going to need less power. So they're going to drain your battery less, and your devices will be hopefully less hot. I think it all depends on what you're trying to build. The more data you're using for training, or the more steps of training, the longer it's going to take, and that's going to get your computer a bit hot. But I would be interested to see on a Raspberry Pi or on an Arduino if it crashes it. That would be a good experiment, actually. But at the moment, I haven't had too much trouble. I've been quite surprised. But again, it's like side projects. If it was for a real application, I would think that a laptop probably wouldn't be enough. I would need like something a bit more powerful. But yeah.
Yeah, your last few minutes sounded like a perfect sales pitch for a new Apple presentation. So, like, you probably know they're switching to ARM processors, telling about with their new processors there will be better neural network processing, better, faster mathematical models. So, yeah, probably
I don't even have an iPhone. Like, I have a Google phone, so I'm not even an Apple person. So.
Me too. I'm also a Google person.
Yay!
Yeah, and the question is like, how how reusable is trained models are. I mean, for example, let's assume you trained your model to detect, like, for example, pouring water or whatever with your microphone. If we transfer it to my laptop, will it work, or it very heavily depends on the quality of microphone and their acoustical features?
So I would say it would kind of depends. Like at the moment for my experiments, as it's in the browser, people are able to just hit the URL on their phone or on their laptop. And most of the time I heard that it was working for other people. Sometimes I think for my Wash OS prototype with the water, I think somebody just, responded to a tweet saying like, oh, it didn't stop the animation when I stopped the water. So sometimes there might be some issues based on the environment that you're in. But in general, for my personal... Sorry.
I don't want to pause you or to interrupt you, but unfortunately we have some timings, and yeah,
Sure, no worries.
it was super rude from my side, but I have a producers over there, and like they are super angry about timeline. Yeah, so
No worries.
thank you very much for your talk. Thanks, Ilya, and for everyone who's watching. You can continue to listen to these answers in discussion zone. Thank you very much, and see you next time.
Thank you.